Hello guys, welcome on Tesla Adventures. Now in this video, following the previous one of the solids, we'll discuss about the Hooke's law. And this law tells us about the relationship of stress and strain, that how does stress vary with the strain for different materials. So let us first of all define the Hooke's law, that whenever stress and strain developed in a body are small, then the stress developed in a body is directly proportional to the strain. And it is very important to note that when we deform a body, then its length changes and strain is developed. Now, the restoring force which is developed in the body to regain its original shape or size is the stress. So, stress is a after effect, and we can say that the stress will be proportional to the strain. So, this is the Hooke's law, and it is only valid for a limited range of stress applied, not for a greater range. So when we remove this proportionality sign, then a constant comes which is elastic modulus, and it is denoted by E. We'll discuss about the elastic modulus in another video, but let us examine the Hooke's law in detail in this video. So it is also important to note that Hooke's law is not a general law, and it is an experimental finding which is valid for only a limited range of deformation. You should know that many materials like elastomers are elastic, but they do not follow the Hooke's law. And the relation of stress and strain for those materials is different, and we'll discuss those materials as well as. Now this is the relationship between stress and strain for let's suppose for a soft iron or a steel wire. In fact, this is for a soft iron. So you can see that till a point which is called as proportional limit, the stress is proportional to strain and they have a linear relationship. So till this point, Hooke's law is valid. So I'll write it down that on this straight line, Hooke's law is valid. Okay, so Hooke's law tells us about the linear proportionality of stress and strain, and this linear proportionality is only valid till this point. So till this point, Hooke's law is valid, and this point is called as proportionality limit. Now, beyond this point, till this point, this is also called as elastic limit or yield point. Elastic limit. In fact, elastic limit is the stress at this point, at yield point. Now, what is this zone? So, in this zone, stress is not directly proportional to the strain. The relationship between stress and strain is not linear, but that doesn't mean that body is not elastic. Body is perfectly elastic in this region also, and body was elastic in this proportionality region also. So till this region, body is elastic, but the variation of stress with the strain is linear till this point. And in this zone, this relationship is not linear, but body is still elastic. So if we supply any energy to the body till this point, then that energy is completely recoverable, and the forces developing the force developed in that body, restoring force, is 100% conservative till this point. Now this is yield point, and this point represents a fact that we say that beyond this point, body solid behaves like a fluid, which means that it starts to flow. Now what does that mean? You must have seen that when we you must have seen any video in which glass is molded at high temperature. So you must have seen that when that high temperature glass is being stretched, then it does not oppose the deforming force, and it starts to flow and like fluid. In fact, flowing means that it is easily stretchable without any oppose. So this point is called as yield point. So we can say that beyond this yield point, the stress developed in the body for a large strain will be very small. So if we apply a large strain, then a small stress will be developed in a body, which means that body is not opposing the deformation, and it is ready to change its original shape or size. So by this we can compare it with fluids. So this is a yield point, and the plastic behavior of the body starts in this region. So this is a region in which if we supply any amount of energy to the body, then that energy is not completely recoverable, and the body which is dragged into this region cannot regain its original shape or size when deforming force is removed. So this is the plastic region. Okay. Now, the forces which are developed in the body in this region are non-conservative, and we have already discussed that energy is non-recoverable in this region. So if this region is long, then that material is suitable to be molded into wires, and we call that material as ductile material, because you can see that if this region is long enough, then it has a long region of plasticity. And for ductile materials which can be easily drawn into wires, we need this property that if we stretch them, they neither tries to regain their original shape or size, nor they breaks down. So this region is long for ductile material, and if this region is short for a material, then that material is called as brittle, which will be broken easily. So this point is called as ultimate tensile strength, which is the breaking stress. You can also call it as breaking stress or tensile strength. Okay, so this point is the highest stress that body can bear, and beyond, if at this point if we stretch the body, then stress in the body will decrease to some amount, and a point will come where that body will break down or it will get fractured. So this was the relationship of stress and strain for a body, and these are all the points which I have already discussed in that graph, and you can take the screenshot of these so that you can remember that. And these are the next points, that breaking stress is also called as ultimate strength or tensile strength. And the soft iron wires have considerably permanent stretch, and therefore they are more ductile as compared to the piano steel wires, which breaks on giving a small amount of strain beyond the elastic limit. Okay, so this is, now we were discussing about the elastomers, and now we will discuss that the stress strain curve is not same for all type of materials. In fact, the materials like rubber and aorta tissue in the heart does not follow this stress strain relationship, as we have already discussed. The stress strain relationship for these type of materials, which are called as elastomers, is demonstrated like that. And these are the materials which completely regains their original shape and size when the deforming force is removed from them, and they do not develop a large amount of stress when we deform them. So these kind of materials are called as elastomers. These materials does not have any plastic region. So what does it mean? That they will not be dragged into that region in which they could not regain their original shape or size. In fact, they can regain their original shape and size from any stage. Okay, so these are elastomers. And obviously, you can see that the relation between stress and strain for these kind of materials is not a linear one. Okay, now what is there are some phenomena which we will discuss for a body, that this is a elastic after effect. So elastic after effect is a phenomena in which you can imagine that if we are stretching a glass fiber on a high temperature, then it will regain its original shape or size infinitely slowly. It will take a lot of time to regain its original shape and size. And this is elastic after effect. And the elastic after effect is negligible for quartz and phosphorus, which means that when we deform a quartz crystal and a phosphorus bronze crystal, then it would regain its original shape and size in a very small time. But it is very large for the glass fibers. Now, what is elastic fatigue? So, elastic fatigue, you must have seen that if you keep on stretching and compressing a spring or a rubber band, then after some time, after multiple attempts to stretch and compress that material will start to lose its elasticity, and you would see that it would have some permanent deformation in it when even on the removal of the deforming force. Now this property is called as elastic fatigue. Now we discuss another property of this graph, which is unload line. So what is this unload line? That if we have already dragged the material beyond the elastic limit is the stress at yield point. You must remember that elastic limit is the stress at this point, which is called as yield point. So if we drag the material beyond the elastic limit and then it is in plastic region, so if we suddenly remove the deforming force, or if we suddenly remove the load and we unload that body, then there is some permanent deformation which is left in that body. So if we have suddenly removed any external force applied on it, then the stress will become zero, but that body will not regain its original shape and size, and there would be a permanent deformation left in that body. So this permanent deformation and this unloading is represented by this unloading line. Okay, so now in the next video we'll discuss about the elastic potential energy in detail. Thank you.